Listen to a single second of any sound, a violin, a voice, a whisper, and what you're actually hearing is a sum. Many frequencies layered on top of each other, arriving at your eardrum as a single moving wall of pressure. On a screen, this is what 1 second of sound looks like. A jagged line, a waveform. You can play it back, you can hear what's inside it, but you cannot see what's inside it. Not in this picture. To pull the frequencies apart, to take a complex signal and recover the individual notes that combine to make it, is the question that all of audio, all of radio, and most of modern physics depends on. It is a question about finding things. Somewhere in a wall of noise from a radio telescope is a planet. Somewhere in the raw static from a seismometer is the signature of a deep underground event. Somewhere in the raw scan from an MRI machine is the inside of a human spine. The signals we care about almost never arrive cleanly. They arrive layered. They arrive buried. The job of finding them, of taking a tangled sum and pulling out its parts, has a name, a formula, and a price. The signal is a sum of frequencies. The trouble is finding them, and for a long time, the cost of finding them was the reason we couldn't. The tool that does this job is called the discrete Fourier transform, or DFT. You hand it a sequence of measurements, n samples taken from a signal, and it hands you back n numbers, one for each frequency present in the signal. Each number tells you how much of that frequency was in there. The mechanism is straightforward. For every frequency you want to test, you sweep that frequency through the signal, multiplying and summing as you go. That last sentence is hiding a problem. To test one frequency, you need to multiply it against every sample in the signal, that is n multiplications. To test all the frequencies the signal can possibly contain, also n, you have to do this n times. The total cost is n squared. For small signals, this is fine. A handful of samples is a handful of multiplications. But the moment your signal gets long, the cost detonates. 1 second of CD quality audio is 44,000 samples. Doing the DFT directly takes nearly 2 billion multiplications. One full song? 8 trillion? A high-resolution MRI scan? More multiplications than there are stars in the galaxy. Until 1965, this was the price. Doing serious frequency analysis on a long signal meant running a single calculation for hours, days, or weeks. There was no way around it. The DFT was a wall, and the wall was n squared. Then 2 engineers at IBM cut the wall by a factor of 50,000. They were not the first to find the crack. It started with a meeting. In 1963, John Tukey was sitting on President Kennedy's Science Advisory Committee. The committee was wrestling with a problem of genuinely lethal urgency. The Limited Test Ban Treaty had just been signed. It banned nuclear tests in the atmosphere, in the ocean, and in space, but not underground. To verify that the Soviet Union was honoring the treaty, the United States needed to detect Soviet underground tests from outside Soviet territory. The way to do that was a network of seismometers, listening for the spectral fingerprint of an explosion. The math was clear, but the computation was impossible. A 1,000,000 sample seismic record meant 1 trillion multiplications, and no machine on Earth could deliver that fast enough to be useful. At the meeting, Tukey blurted out an idea. The man sitting at the same table was Richard Garwin, a name not many people know now, but the most consequential physicist in the room. Garwin had designed the world's first hydrogen bomb at age 23. He understood instantly what Tukey had just said. Garwin took the idea to a programmer at IBM named James Cooley. He did not tell Cooley what it was really for. He told him it was needed for a problem in 3-dimensional crystals of helium-3. Cooley wrote the code believing he was helping a condensed matter physicist. He didn't learn the truth for years. The 1965 paper was 5 pages long. The algorithm took the cost of the DFT from n squared down to n times log n. For 1,000,000 samples, that is a 50,000-fold speedup. But Cooley and Tukey didn't invent the algorithm. They rediscovered it. The original was 160 years older, and its author had filed it away in Latin as a curiosity. Here is what the algorithm does. When you compute the DFT directly, you treat all n samples as one block. and you sweep every frequency through the whole block. That is the source of the n-squared cost. But the DFT has a hidden symmetry. The samples can be split into two groups, the ones at even positions and the ones at odd positions. And it turns out that the DFT of the whole signal can be rewritten as the DFT of the even indexed samples plus a simple twist applied to the DFT of the odd indexed samples. Think about what that means. A DFT on n samples, which costs n squared, has just been rewritten as two DFTs on n over 2 samples. Each of those costs n over 2 squared, and there are two of them, which adds up to n squared over 2. The work has been cut in half. Now apply the same trick again. Each of those half-size DFTs splits into two quarter-size DFTs, then eighths, then sixteenths. Each level cuts the remaining work in half, and there are only log n levels before you reach DFTs of size 1, which are trivial. At every level, the work is n. The number of levels is log n. The total cost is n times log n. The atomic computational unit at every level has a name, the butterfly. 2 inputs, 1 rotation, 2 outputs, the sum and the difference. The data lines cross each other into a shape so distinctive that the entire diagram of an FFT can be read by sight, not by formula. For 1 million samples, the algorithm collapses 10 to the 12 operations down to 20 million, the difference between a week of computation and 1 second. This is the algorithm that detected nuclear tests, runs your phone call, and reads your MRI. It was first written down in a notebook nobody read. Once the algorithm existed, it spread everywhere. Every Wi-Fi packet your phone sends or receives is encoded by an inverse Fourier transform at the transmitter, and decoded by a Fourier transform at the receiver. Every 5G symbol is a 4,000-point FFT. A modern phone in active transmission runs one roughly every 35 microseconds. Every MRI scan ever taken acquires its raw data not as an image, but as the Fourier transform of an image, with the inverse FFT performing the actual reconstruction. Every JPEG photograph and every streaming video uses a Fourier cousin to compress small blocks of pixels. Every MP3 song, every voice call, every gravitational wave detection at LIGO, every satellite radar map of the surface of the Earth, even cryptography depends on it. The fastest known way to multiply huge numbers, the kind used to generate the keys that secure your bank, is built on the FFT. In 1994, Gilbert Strang of MIT called it the most important numerical algorithm of our lifetime. Looking at the count of how many FFTs are computed every second around the world today, roughly 5 billion phones, each running thousands per second, before counting servers, satellites, and scientific instruments, that claim is not poetry. It is a measurement. The FFT is, with reasonable confidence, the most executed non-trivial algorithm in the history of computing, and we have only known about it in its modern form since 1965. Cooley and Tukey published in that year. The algorithm itself was first written down in 1805 in a notebook nobody read, Brunswick, 1805. A 28-year-old astronomer named Carl Friedrich Gauss is sitting at a desk working on the orbits of 2 newly discovered objects, the first asteroids in human history. Pallas, found by Olbers in 1802, Juno, found by Harding in 1804. To pin down the path of a new asteroid, you take a handful of measurements over several months, and you fit a smooth periodic curve through them. 12 observations, a trigonometric polynomial, a piece of mathematical drudgery that takes weeks of pen and paper computation. Gauss notices the structure. He notices that the work, when n is 12, can be split into a 4x3 computation, or a 3x4 computation, by exactly the trick that Cooley and Tukey will write down 160 years later. He works it out for the asteroid Juno. He writes it up in Latin in a manuscript he titles Theoria Intapollationis Methodo Nova Tractata, a theory of interpolation, treated by a new method. He files it away. He does not publish it. He does not tell his correspondents. He moves on. The manuscript stays in his desk for 61 years. It is finally printed in 1866 as the 3rd volume of his collected works, after his death. By then it is treated as a forgotten technical note, of interest only to historians of science. It is the same algorithm, identical structure, the recursive split, the mixed factorization, the rotation factors. All of it in clean Latin, on a sheet of paper that no engineer, no computer scientist, no signal processor would read for more than a century. He didn't think it was important enough to publish. So why did the world have to wait? The answer to the question on the screen is simple and a little bleak. Gauss had the algorithm. He just didn't have a use for it. To do 12 observations by hand takes a few hours instead of a day. The savings are pleasant. They are not transformative. The algorithm only matters when there are things, many of them, vast amounts of them, to push through it. Before electronic computers, there were no signals long enough, and no problems large enough, for the speed up to be worth the effort. The algorithm was correct, it was beautiful, and it was useless. Cooley and Tukey didn't invent a smarter idea than Gauss had. They invented Gauss's idea at the moment a transistor could run it. They handed it to a world that finally had something to give it. The man who coined the words bit and software gave us the algorithm those bits and that software exist to run. The man who designed the first hydrogen bomb walked it into existence to detect the next one, and it had been quietly waiting in a drawer in Brunswick for more than a century and a half. 2 centuries after Gauss filed it away, a version of the same algorithm is what pulled the signal of 2 black holes colliding out of the static of a distant detector. Most algorithms get faster over time. This one was always fast. It just had to wait for the world to be ready for it.